Hi everyone, welcome to the third Dutch Data Systems Design Seminar of 2023. We have two very interesting talks today, and the first talk is going to be from our local speaker, Till Dömen, who's a PhD student in Aachen, a guest researcher at the UvA, and also an engineer at Hopsworks. And he's going to talk to us about a large data sets of relational schemas that he crawled from GitHub when it was still possible.
Indeed, yeah. Thank you for the introduction. The talk is called Database Schemas in the Wild. What can we learn from a large corpus of relational database schemas? So, and that's also the question we ask ourselves, or I asked myself when I started this project. But basically, 2 years ago, I started just into the blue, inspired by Madelon's work on GitTables. To crawl schemas from GitHub, and that's basically how this project started. And I'm going to share a bit about the process of like how we acquired these schemas, what we did with them to extract structured schema information from them, and then what kind of use cases we looked at that we could use this data set for, and also what we think could potentially be done with it in the future. So one of the motivations for it is that there's not much public data available about how databases are structured in the wild. So it's hard for companies, of course, to publish. There's no incentive for companies to publish the schema of their proprietary databases, and also there are, of course, lots of data protection concerns and so on, intellectual property. So that's why there are just not so many real-world databases out there available for researchers. So, and that's also I just collected a couple of papers basically that relate to this problem. One of them is by from Tabular software. So they basically use data from their own data warehouse to see how workloads on this data compare to workloads on a traditional database benchmarks, and show there's a discrepancy between real-world workloads and workloads we usually test databases. So, and another extract from a paper that's called SchemaDB. That's actually quite similar to what we did. Those researchers also looked at schemas in GitHub, extracted them from SQL scripts. Right around the same time, we started doing this as well. It seems that people think alike sometimes, and so but they said, also it's hard to find this data because it's usually not shared for privacy and security concerns and so on. And another one is from a paper from 2021 about benchmarking feature type inference. And to train these feature type inference models, the researchers also needed training data, and this was, again, hard to come by, especially this true in the wild data. So why do we need such data? And that's from my perspective, because that's more in my research area. I'm interested in developing tools to support people doing various tasks with databases. And when you ingest data, you might want to put constraints on the data, but it's tedious to define them, right? And so it would help to have suggestions that should suggest useful constraints for the data that's in the database. Or if you have a couple of tables and you want to connect them with foreign keys, it might be interesting to have suggestions for that as well. Or for automatic data integration, for data augmentation, foreign key detection is also a relevant problem. And there's currently need for data that can be used to train models that are good at detecting which columns refer to each other only based on their name, for example. It's really hard to come up with good rules for that. It's better to use language models to learn those things. Bit of a different problem is header detection in CSV files. If we would just know how headers of tables usually look like, what we could easily learn from a large data set of real-world databases, we could quite easily say, okay, the first row is probably the header because we've seen this type of header in a lot of different tables. Yeah, and then beyond that, of course, if we have seen, if a machine learning model has seen a lot of different schemas and tables, it could even help with auto-completing schemas, like suggesting additional columns that could be useful for a table and so on. Another aspect that goes more into the direction of the Tableau paper is maybe from the way people design databases, we can learn about how they are using them and make better design decisions for building database systems. But the first part will be what I'm going to focus on in the talk. So to summarize again, like what is currently out there, we have this web tables or GitTables corpus, so large corpora of single tables. And on the other hand, we have smaller corpora or smaller corpus of real relation tables, full databases, different tables in there connected with foreign keys and so on and so forth, but they are only like a really nice data set is this CTO Prague Relational Learning repository, but it has only around 100 databases. So it's not in the order of magnitude that we need for training machine learning models. So yeah, our solution to it is to have this Schemas data set that is much larger, but has then the drawback that it doesn't have the data, because even on GitHub, we cannot find large databases with the actual data content. Also, GitHub is probably not the right place to store such kind of data. And yeah. So a bit about how we created GitSchemas. So this was something which was working when I started this work. Nowadays, this probably wouldn't work anymore because GitHub restricted their API access, but we use the GitHub Search API to find basically all SQL files on GitHub that contain gray table and foreign key statements, and use that as a filter because I think there were around 30 or 40 million of these SQL scripts on GitHub. And we use that as a filter to narrow it down to basically only data definition language files that contain data definition language. And then we used an SQL parser to parse these files. On the next slide, I will show a bit about like the SQL parsing step. And then we extracted structured JSON data basically from it that contains tables, columns, constraints on the columns, and so on. And that's basically all there is to it. And what we get is a quite diverse data set that covers really like enterprise typical data, I would say. So the most common table names are users, employees, departments, salaries. Of course, in parts, they might come from like example databases. There are a lot of projects on GitHub that contain like, okay, this is your starting point, this is a simple schema, and that's probably also coming from these kind of examples, but still we see that there's a lot of diversity as well, or it's very refined what kind of columns, for example. Yeah? These are all the different columns in a data set that start with user, or an extraction of that. Or when you look at the random sample, you see there are a lot of different domains covered by it that I would say that you would typically expect to find in an enterprise-like database. And also it aligns well with findings from related work. So that's actually from the Tableau paper where they looked at the Tableau warehouse and the distribution of data types in there. And this is not really nicely cleaned up. So the types don't exactly match one-to-one, but you can see that the varchar type, so string columns are the most prevalent in the GitSchemas corpus, and that's the same for the that's the same thing that the Tabular researchers found, that string columns are quite common. Next are integers and so on. So it lines up really well with what real enterprise database contain. So now a bit about the parsing. So we started with using standard SQL parsers like pglars, and the success rate was quite low in parsing the different schemas because, of course, they come from a lot of different databases. And that was a challenge because we wanted to extract as high quality data as possible. We could have maybe used a large language model to do the parsing, but then we wouldn't really know if the collected data is accurate or not. So wanted to use a real parser for that. Ended up using this simple DDL parser, which is basically specialized to parse exactly this kind of data definition languages across different SQL dialects. And we're still working on improving that. There are a lot of bugs that we could basically find in this parser by just throwing the GitSchemas SQL files at it. We have one master student who is working on basically increasing the success rate of the parser we have and to identify what are the challenges where you have such a diverse corpus of SQL files where you're not really sure where they come from, what database system they're written for. To find the best way to interpret them. So, and now that's basically the result of the work. That's how some summary statistics about the corpus that resulted from it. So could collect in total 155,000 schemas that contain 1.2 million tables roughly, 7 million columns, almost 600,000 foreign keys, and these different properties, which we can also look at some unique counts. We see that, for example, even for the database checks, for the table checks and column checks, we have at least 8,000 examples of what checks people implemented on their database count. So this could be really interesting also to learn patterns from it, to generalize from this to more generic rules on how to maybe suggest checks for database columns, for data quality validation, for example, to derive useful checks. If you have a column that's called zip code, and we find a lot of checks for zip code columns in there, we could, draw data quality constraints from that. Here's an example. That's how the table checks. It's a subset of the table checks. So it's really, it might be obvious that price should be larger than 0, but it's really hard to come up with such a rule without either having human guidance or a training data set like that. And these are the number of instances. So we also have some indication of how often these kind of checks are used.
Did you try to train a large language model on this corpus?
Not yet, but that's of course in the plan. No question. Yeah, that's what it's all about. Same for foreign keys. Just a couple of examples, but that's exactly what I want to get at. So we looked at the foreign key detection problem with GitSchemas and large language models. And so this is just an example. This is something I did with GPT-3. So this is the prompt. It describes 2 tables and then starts specifying a foreign key relationship between the employee and the salary table. So now we can use GPT-3 to predict which column in the employee table this salary employee ID refers to. When you look at it, it's quite obvious that it should be ID. Right? But to come up with a generic heuristic to do that is quite hard. But the language model is quite good at it. So it predicts ID out of the box. But how do we know like how well it does overall? And that's exactly what we can. Sorry, this one. Right? Can large language models can autocomplete SQL statements, but can they really? Right? So that's basically the question. And something's wrong with this. Sorry. Yeah, so that's where you can set up like a simple experiment and say, okay, we sample foreign key relationships that we know from GitSchemas and generate these prompts and see what the large language model predicts. And then we can just evaluate because we know the ground truth from our GitSchemas corpus. And then we can see that GPT-3 has like 81% accuracy on this task. So accuracy means it always makes some prediction, and we just check whether that's the right or the wrong prediction. And now we can improve upon that because we have training data, right? High quality training data. So we use a smaller T5 model to fine tune it on exactly that task, and then can achieve a higher accuracy on the same task with a smaller model. And and that's only using the schema information, right, to predict the key. That's not yet using data content. So it could be just one indicator in a hybrid method that also looks at things like set intersections and so on. Yeah, we're planning to evaluate that. And this hybrid method. And another example is now the CSV Header Detection I mentioned. So what we do here is basically what I described earlier. We just built a classification model that takes the row of the data, it concatenates it as a large string, and then we just feed it into a BERT model and have a binary classifier there which says, okay, this is either a data row or a header row. And we fine tune it on I think 20,000 samples from the GitSchemas corpus. And then we evaluate it on a test data set of CSV files. When we use like the pandas library, it's right at 80% of the time. It always uses the first row as header. So, but then when we add the signal from this classifier, we can also increase the header detection rate, as you can put this problem. Yeah, I think there are a couple of more things that can be done, and these are the things we're currently working on. Still working towards a full paper for that. So these are things we would like to have in there. So this foreign key detection method, as I said, would be nice to combine with a data-based method that actually looks at the distribution of values in the tables and only uses the signal from GitSchemas as an additional signal to the prediction. And data type and constraint prediction are something which I think would be also quite straightforward, since we have the data types and constraints in the corpus. And schema completion is something that I think is also interesting, and it fits in really well with large language models. Just predict the next token when you give it like the beginning of a schema. I expect it will do pretty well with also completing the schema with useful codes. As a conclusion, I think it's like I hope the main takeaway from it that this schema dataset, even though it doesn't contain database contents, only the schemas of tables can still be quite useful for a variety of tasks. Like even for testing the SQL parser itself, we also release a subset of the permissively licensed files we call that we can just share. So that we can also share the raw SQL input. And yeah, we can benchmark how good large language models are at writing SQL code, essentially, or subtasks of it, like foreign keys, and the use case I described earlier. And yeah, I think still a lot of these approaches would benefit from a hybrid approach where you train your model on part of your model on GitSchemas and another part on actual table content from datasets like GitTables. Yeah. And I think that's it. That's the paper, a workshop paper from ICDE last year. If you're interested in reading more about it, so that's still based on older iteration of the data set, but it's already publicly available. And yeah, that's the GitHub link. So thank you.